Fair enough. Fair enough. Ugh. Ugh. Hey, hello. Just getting ready. How you doing? Ali said you were coming. Let me just get that on my phone so that I can, come on, I can work out what we're doing. What's going on? What's going on? That one. No, I don't want an advert. I want that full screen. Oh, don't matter. Okay, I'll use my other clock. How are you? You can, if you like. I'm hoping that the you can see my screen. I've got the chat there. I'm hoping you can see that. So what I'm going to do, oh, Ronnie, what I'm going to do is move that over to my other screen. But what I want you to do is, because I know you're new to this, is if there is anything that you are not happy with, then please put it into the chat or unmute if you like, and I can respond straight away because it's just by my camera over there. Okay, for everybody else, what I'm going to do is Ali has started the rota at the beginning, which is maths for physics. So I'm a sneaky suspicion one of you has come to the maths for physics, which we ended on at the end of 2024, sort of. But if we're going to redo it, I'm sorry about that. But again, if there's anything that you wish to pause on or ask questions about, then please do so. Okay? I hope we're all happy with that. You can write something in the chat if you like, but it doesn't really matter. Okay, let's give it a go. So what we're going to do now is to start with maths for physics. So you lot obviously just romped through your physics GCSEs. You loving your year 12 stuff. Your maths GCSE, I'm hoping, didn't cause much of a stress at all, and you are possibly almost certainly doing maths A level with your physics. So what we're trying to do is to concentrate on those little bits that cause the problems. Okay, those bits that cause the problems. And year after year after year after year, if you read the examiner's reports, because I have for you, so you don't have to, they come up with the same old guff every single year. They say it is surprising how many people slightly don't get it right. Okay, so you lot have got your specifications. You know which specification you are doing, and you are going to download it, and you are going to cut out from your specification the content, the physics content. I don't care about the AOs, I don't care about the when you can redo it and the shelf life of it and how you do your practicals. Yet all I want you to do is to download the content, because that is what you are going to be examined on, nothing else. Not what your physics teacher liked because they did an MSc in it, not because they like it because they read a book about it or something like that. And, you know, physics teachers surprisingly are human beings, and they tend to dwell on stuff that they like. For instance, I do not like particle physics. I've taught it once in my life. I don't like it. I always give it to my colleague who we are sharing the class with. He always does it. And I know that Ali loves particle physics. It's her bag. It's not mine. Okay. So if there's any particle physics stuff, Ali Camacho is the person to ask about that. I like me waves. I like me electricity. I like my circuits. I like radioactivity. I like that sort of thing. But hey, find your specification, whichever one it is, download it and find out what you need to know. Because in it, there is obviously a lot of maths. Physics contains 40% maths, chemistry 20, and biology 10. So physics is pretty maths intensive. So you will have got your calculator, and I don't want to annoy you. I do not want to patronize you, but it's really important that you know how to use the thing. Okay, there's one thing which I've seen year 13 students do, and it winds me up. It winds me up, okay? But you lot are better than that, and you won't have that problem. So we'll come back to calculators as we go. In the specifications, when they were being designed, somebody above the exam boards said, you must put this maths into your physics. All of your exam boards, all of you guys, you've got to scuttle off and design a specification, but it must have this maths in. So the maths is common to all specifications. So if you look for the appendix at the end, it's about maths in your physics course, it will be the same, just like the practicals. So in OCR, they talk about the mathematical requirements. There are all the AQA pages on maths. So if you are doing AQA, I know a lot of you are, then you've got to go to those pages there and make sure that you can do all of that. There are some little surprises in there that catch people out if they have not done that. There are questions that appear occasionally every year or so, which you think, oh, I have not got a clue how to do that. And yet, when you're shown how to do it, you go, oh, that was easy. So make sure you understand that. Okay, so what we're going to do is look at mostly the stuff that is not in bold, but possibly when there's time at the end, we are going to encroach onto that other little topic, which comes up towards the end of year 12, and it is throughout year 13, and it freaks people out. It freaks people out, and it's a subject of exponential functions and logarithms and natural logarithms. So what I'm going to try to do is sneak in a little bit of that. So when you come to do it, you'll go, oh, got it. Okay. Or I understand this. Let's get on with the practicals or something like that. Okay. I think it is something that you need to have a feeling about before you actually meet it in anger with real physics problems. Right, here is the EdXL stuff, and much to your surprise, it's exactly the same. Those, you know them, okay? The ones which are which are shaded, those are the ones that crop up a lot, but I've put a red ring around the extra little ones, the picos and the femtos, because they crop up in particle physics and particle interactions. But I'm guessing by now in your year 12 course, you will have done the, pardon me, you will have done the strong nuclear force and its range, the femtoey stuff down the bottom. Standard form. Standard form. Now this surprised me when I found out about it. when you use your calculators, you need to know which buttons to press. Now, this is a thing that I was saying at the beginning, I find quite astonishing. If and you're not, okay, you are not like this, but if you are, you're not going to be for much longer. If you type this into your calculator, that's what you want to put in. You want to put in 3 times 10 to the 8, the velocity of light. What you do is, and I've seen people do this. Okay, first of all, I'll say what is right. You do 3.00, if you like to put the zeros in. Then you use that guy there. Then you use that guy there. Or you use that guy there. And then, so it is, I'm going to take this one, exp 8. That is 3 times 10 to the 8. That's how you do it. Okay. I'm going to say what is wrong now, and it's what teachers shouldn't do. It's what teachers shouldn't do, because there's always somebody at the back of the class who's looking out the window, not quite sure what's going on, vaguely is listening, and then listens to the bit that I say, which is actually wrong. So I'm going to say this is wrong, and I know you are concentrating. What you don't do is do this thing. You don't do this. You don't do 3.00, then that button there, then that button, times 10 y to the x, then 8. You don't do that, because that is something different. But I'm sure that you don't. I'm sure that you don't, but I have seen year 13 kids doing that. Please don't do that. Please don't do that. Right. Now, this standard form thing, right? These are, now what I do, for those that don't know this, is I take actual A-level graphics 99% of the time, and I take A-level questions 100% of the time from various exam boards. I take the mark schemes from those exam boards. I don't do it myself and make it up. I use the mark scheme because the examiner is going to use the mark scheme. And I always look at the examiner's report, which makes me go, oh, that's what they're looking for. That's interesting. So that I can feed that back to whoever I'm teaching so that they will know what's in the examiner's heads, because that is what you have to do, not what's in your physics teacher's head or what's in what looks good on paper. You've got to play the game. This is a game. It's a game. And you've got to know what they want. And you've got to be able to write it down, send it off, jolly good, tickety tick, off you go, get your grade, do what you want to do. This amazed me, because one question said, give your answer in standard form, you know, the sort of GCSE sort of stuff. And that was the actual answer, 1.63 times 10 to 3 newtons. That, as you know, is standard form. Watch this. Those were not. I think that's kind of harsh. That's kind of harsh. But again, that's what the examiner wanted. If you write that down, you think, well, it is tough poops. You're going to get it wrong, because that's what's in the examiner's head. And the bottom one, I think, is particularly unpleasant, 1.63 kilonewtons. I mean, all of those are that number at the top. They are 1,630 newtons, but that's what they want. So that's it. Sorry about that. So that's your standard form. We're going to get on to exponentials later, so we're not going to spend much time on that at the moment, but it is those buttons there. Those are the buttons you use when we do our exponential powers, and we'll do them in a bit. Right, little pause there, because now I'm going to show you something that really winds the senior examiner up, and it's this. It's this. Okay. You know that you are going to measure the cross-sectional area of a wire. You know that you are going to measure the cross-sectional area of something big, like a reservoir or something like that. And sometimes you are given quantities which aren't in SI units. Now, the meter is the SI unit. Okay, we know what a meter is. And it has been divided, when appropriate, into 1,000 equal spaces called a millimeter. Okay, millimeter, a thousandth of a meter. So there are, and I'm looking at the thing here, I'm looking at the chat. If you want me to go faster, then please say so down there. If you want me to redo something, say so down there. If you want to unmute, do that. I'm happy to do that. Right, so there is my meter. There are 1,000 millimeters along the top. There are 1,000 millimeters along the side there, which begs the question, how many square millimeters are there in a square meter? Well, it's 1,000 times 1,000, which is 1 million. There are 1 million of them, okay, which is 10 to the 6. So what I'm saying, get that sort of in your heads, get it over here, keep it in your heads. Because when you are doing an experiment, say you're doing resistivity, and you've got to calculate the resistivity of a piece of constant 10 wire that's on the desk in front of you, and you take the diameter and all that sort of stuff, and you work out what the area is, do not be surprised when you get something times 10 to the minus 7 meters. It is small because a square meter is big and a wire is very small. So think what you get. Think, get an answer, pause for a minute, look at the answer, go, yeah, that's about right. That's about the cross-sectional area of a wire. Okay, and then you can carry on and do the rest of the question. In the beginning of the AQA, it says, I should have got the slide and put it here. It says that you need to have a feeling for typical, oh, what does it say? What does it say? Something like the size, the magnitudes of typical quantities that you experience in the specification. Okay, so in other words, you need to know the classic is the speed of somebody walking, the speed of somebody running, the speed of somebody cycling, I think, something like that. Or, you know, as you go through, you'll be working these things out and bear them in mind. You need to know the mass of a person, because what the questions say, very common multiple choice question, is what is the typical kinetic energy of a walking person? And you go, I have no idea. I have not got the foggiest idea what that is. But you will have if you go, oh, I've just done a question on a human being. Mass is about 60 kilograms, might be 70, don't care. Something like that. It's not 1 and it's not 18,000. It's about 60 or 70. How fast is somebody walking? Well, I don't know, 4 meters a second. Let me think. Yeah, in that sort of time, you might walk 4 meters. And then what you do is you put it into half mv squared and you get a value and it will correspond to one of those roughly. I mean, obviously, people are different. They walk different speeds. So you're going to get different values, but there will be one which is within an order of magnitude of being right. Quite often, people don't get those questions right. So as you go through, get your quantities, think, oh, that's a resistivity of a metal. All right, that is a density of concrete. Fair enough. That is the diameter of a planet. All these things, just get a rough idea for what they are-ish. So that's my area. Let me get rid of that and let me go to the next thing. You've guessed it, is volume. How many cubic millimeters in a cubic meter? The answer is 1,000 million, or 10 to the 9. So how many meters cubed in a millimeter cubed? 10 to the minus 9. Okay, it is a billion. Yeah, quite small, isn't it? Okay, now, where does that come into its own when you are actually doing a question? Well, what I'm going to show you, as I said, is an actual physics question. I was amazed when they had this. I was amazed. Anyway, I'll shut up while you can read that. Yeah. Okay, so you might have done this, doesn't really matter. I'll tell you how to do it. You've got to calculate the area under that line. That's what you have to do. Now, not got a clue how to do that. Not got a clue. I know what I'm going to do. I'm going to turn it into a triangle, because I can do triangles, and I'm going to sort of go from there up to about there. That'll do. And from there down to about there. Yeah, that'll do. And then I'm going to do half base times height. Okay, and that's easy. I hope you don't mind me saying so. Area of a triangle, half base times height is easy. But look at that scale on the left. What were they thinking? What were they thinking? If you did that scale, if you handed me that graph with that scale on, I would say, you've got to be joking. You're having a laugh. Do it again and come up with a good scale. But anyway, that's what they chose. You can't argue with it. So I've done it for you. The top of the peak thing is 1,840 newtons. And the, oh look, there we go. What a joker. What an absolute joker. They have given you milliseconds like that. So that's a little problem. So you've got to keep your eye on the scale so that you know that it is thousandths of a second. So you've worked out your change in momentum. Fantastic. And then there's something to do with stress. So there's a bit of a force going, there's a bit of a formula going on here. Stress force over area. If you don't know, it's on the formula sheet, but you might have done Young's modulus by now. And you know that stress is force over area. So there is the area, 550. You spotted it, millimeter squared. So you've got to turn that into meter squared by dividing by 1,000,000. 1,000,000. Yeah, that's it. Find by 1,000,000. And so that's what I'm saying. That's when you've got to be sort of on your toes when you're doing this sort of thing. Hopefully that's all okay. Everything in the chat looks quite good. I'm enjoying that. Everything in the chat is quiet. So let's go on to the next bit. So here's our examiner's report. Converting the cross-section area of the chord from millimeter squared to meter squared caused some problems. Really? Really? Okay, every year something like that crops up and I think, really? But please, please, please try super hard to be okay with those. Right, now we're moving on to these things called degrees and radians. In the specification, it says, I'll show you a little bit about what it says. You need to be able to use degrees and radians. So what I'm going to do is move on a little bit to do a little bit of end of year 12 sort of stuff. I'm going to come back a bit and do another equation. I'll come back to that in a minute. Okay, degrees and radians. So on your calculators, again, people get caught out by doing this. There it is. In this Casio calculator, when you set up its mode, you can set it into number 3 degrees, number 4 radians, or number 5 gradients if you have a death wish. But don't use gradients because they're a weird American thing. 100 gradients is a right angle, but we're not doing those. They're bonkers. So let's go with degrees and radians. So usually when you are resolving forces, you use degrees. When you've got angles and you're trying to use degrees. But there's a sneaky little thing called a radian, which is a different way of measuring angles. So I'm going to just go on and talk about radians now. If if in the chat all of you say, I've done radians, let's move on, then I'll move on. But let's see. Okay, so a radian is a unit of angle. It's a measurement of an angle. So let's have a circle. Let's have something, don't care what it is, car going round the roundabout, planet in its orbit, whatever. Let's say it's going from A round to B like that, and it's going that way round. So as it does, what it does, it subtends an angle theta at the center of your circle. So I can see you now, you're twitching, you want to get your protractor out, slap it on the screen and measure the angle in degrees. 20-ish, I don't know, something like that, maybe. Okay, and you would be right. That is the angle in degrees. Looks like about 20. But I want to do this in radians. So let me get rid of those and put some distances on. I'm going to say that the thing, the planet, whatever, has moved from A to B along the arc length S. It's going round in a circle along the arc length, and it's gone round a distance S. Now, the radius of this circle is R. Okay. Now, I'm going to say it is blindingly obvious that if you have the same R and you double S, then you double theta. It's obvious. Just look at it. If it goes twice as far around the circumference of the circle, then theta is going to be twice as big. It would go from 20 degrees up to 40 degrees. Okay, let's not talk about degrees anymore. Let's talk about these radian-y things. So there is some way of measuring the angle theta, but not in degrees. And it's this. It turns out that if you say theta, the angle, is simply the arc length divided by the radius, makes sense, doesn't it? You double S, you double theta. Brilliant. And the units now for theta are the radian. That's what it is. That defines the radian. So the degree is 1/360th of the way round a circle. Why 360? Because it's divisible by 1, 2, 3, 4, 5, 6, 7, all those sort of numbers, not 7. It's divisible by a lot of numbers. So when people were thinking about what units we use for degrees, they came up with that number because it has lots of factors, I think they're called. Okay, whoopie-doos, whoopie-doos. That's not very natural to me. The number 360 doesn't feel nice to me, but this does, because this doesn't have a unit. You don't have a unit. If S is measured in meters and R is measured in meters, then you have meters over meters cancel out. It does not have a unit. It's beautiful. It's absolutely beautiful. And maybe they should have started with radians and we wouldn't get in this mess and have these weird things called degrees. But hey, we're stuck with them. We understand them. But now let's look at these new guys because they are more beautiful. Let's have a think. So I want to give you an idea, as I said before, of what angles are. Okay, you know the mass of somebody, you know somebody walking, sort of thing. So let's have a look. So let's say I want to know the conversion between radians and degrees. So 360 degrees is all the way round a circle. Okay, that is all the way around the circle. So I'm now going to work out how many radians there are in one complete revolution. So, year 5 maths, could be year 6. It's definitely before year 7. The circumference of a circle is 2 pi r. That's S, the distance all the way around. But in radians, you divide by r because that's how you define the radian, which gives us, oh, look, there you go. And you get 2 pi radians. So 2 pi radians is 360 degrees. 180 degrees is 1 pi radian. So what should I do? What should I do? I'll do. So 1 radian is 180 over pi, which is about 57 degrees. Okay, I've done this before. I don't have to calculate it. So if you imagine, let me just draw this. Why didn't I do this? Let me draw this. Let me draw something which is about 57 degrees. Did you say that's about 50? A bit less than the right equilateral triangle? About there. That looks about right. So as I've drawn it there, that distance there, bump, is about the same as that distance there. If so, then that angle is 1 radian. Yeah, that's about right. Okay, that's what a radian is. Now, the beauty of radians comes into its own when you look at small angles. Okay, you've got to know that. Okay, So what I've done is, because I like doing this sort of thing, I have written myself a little spreadsheet which calculates angles in degrees, radians, and giving you the sines, cosines, tangents of them too. If you use Excel, and you will use Excel, I've said this a million times, you must use Excel, because later on I'll show you some questions which actually say, has this person ever used Excel in their life? You've got to use it. So when you're doing some practicals, it's in the CPAC to make sure that you've plotted your results using Excel, a graph or whatever, analyzed it, looking at intercepts and gradients. It's brilliant. It's absolutely brilliant. I love it. Anyway, this is what I've done. I've put those numbers down the side that you saw before, which were the mathematical requirements. So you've got to know it. You've got to know it. Okay, so here is the angle. There it is in degrees there. Okay, because that's what it said on your specification. Then what I did is, if you look up at the formula up at the top here, I divide, ooh, blimey, oops, 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 oops. I've messed it up. I've messed it up, right? If you look at it there, what I've done is divided the angle 45 degrees by that number 57, point whatever it is, and that gives us the angle in radians. So 60 degrees is a little bit over 57, 1.05. Because Excel does, if you use the trig functions, it's a natural thing. It likes it. Excel uses the angle and assumes that it is in radians. So if you ever do any trig stuff with Excel and get weird results, it's because you've got to convert it to radians before you do any sine cosine stuff. So there's your sine theta when theta is in radians. Much to your surprise, 90 degrees. Oops. Oops. 90 degrees. There it is. 1.57 radians, which sine 1.57 radians is 1, because sine 90 is 1. Okay, that's what you need to do. Have a play with Excel, if you like, so that you can, if I go back now, if I get rid of that and go to there it is. Right, you've got to know those things. Now, something else astonishingly beautiful about radian measure is something magic happens when the angles are small. Something magic happens when the angle is small. So when you do simple harmonic motion, you are going to get your pendulum and you are going to swing it, and your teacher is going to go, make sure it swings with a small angle. And you're going to go, why? And he's going to say, well, just do it. Maybe they'll say, because when we get the formula, which I'll show you in a minute, it only works when theta is small. It only works when theta is small. And what happens is when you take your resolving your forces, which I'm not going to do now, if you don't mind, but what happens is, what you have to do is, when you resolve your forces, there is a sine theta involved in it. Okay, when you look at a small angle, if you look at sine theta, sine is SOHCAHTOA, sine opposite over hypotenuse. I didn't know that, I was just being an idiot. You do this, you do this. Sine is opposite over hypotenuse. So sine theta equals opposite over hypotenuse, opposite over hypotenuse. Now, that when theta is small, I'm going to botch this. I'm going to say that is a hypotenuse as well. Okay, when that's 90 degrees, if theta is small, forgive me, please, forgive me. I'm going to say that is 90 degrees as well. So your sine theta is opposite over hypotenuse, which is opposite over hypotenuse, which is radian measure. So if theta is in radians, then sine theta equals theta, but only when it is small. That is the beauty of this thing, but only when it is small. So let me go back to this thing here, my spreadsheet. Let me go back to my spreadsheet here. Where is it? Oh, yes. When I go back to my spreadsheet, if I have this, so there is my angle 1 degree. So when it's 1 degree, sine theta is 0.02, cosine theta is 1, and tan theta is that. But what you get is sine theta divided by theta. The difference is going to be 0%. Okay, if you do it from 1 degree, the difference is 0%. 10 degrees, then sine theta and theta only differ by 1%. And it's that that makes that formula work. That formula that we're going to I'll show you for a pendulum only works when sine theta equals theta. And if you twang it out 10 degrees, which is quite a lot really, then the formula is going to be 1 degree not quite right. Okay, if you do it 25 degrees, it's only going to be 3% difference. Spreadsheet worked it out. But it is important that you use that small angle approximation. That's what it says for AQA. There you go. So I've taken the chunk from the specification, and the stuff on the left is what your teacher is going to try to get you to understand. But when you look at your spec, because you're professionals, you're going to do this, not many other people do. Have a look at the other stuff around there. And then the right-hand side for AQA, they give you some little hints. Students should recognize the use of the small angle approximation in the derivation of that formula T equals 2 pi root L over G. So you are going to have to know that that is the case. Okay. And then for your maths skills, there it is. You need to know that sine theta is about theta, tan theta is about theta, and cos theta is near as darn it 1 for small theta where appropriate. That could crop up in a multiple choice question. The examiners are very, very, very clever at picking little bits of the specification and turning them into a question. And what's really good fun for me, bit geeky, is to go through an exam paper and find out where the questions came from which minute little bit of the specification. And if you haven't done it, then you might not get that right. So if you do all of it, then you stand a greater chance of getting the results that you deserve. Right. I'm not going to actually do the derivation now because I've just seen what the time is. I mean, I'll leave that to your teachers. And there is the angle stuff. There's my spreadsheet, and it tells you, I've just shown you what I've had before. Right. Next thing. What? Calculate the largest possible distance in meters between the Earth and this astronomical body called Vesta. So the smallest is there. There it is. Let me just do this. The smallest is, the largest distance, sorry, is there. Okay, so that is what the greatest distance is in astronomical units. But on your formula sheet, they give you what the astronomical unit is. So you simply multiply that by that and you get the answer in meters. And spookily, that's worth 2 marks. I think that's quite generous. Now, this is where we've got this angle subtended stuff. So show that when Vesta is at a distance of 1.73 times 10 to the 11 meters from the Earth, the angle subtended by Vesta, which has a diameter of that, there we go. So here is Vesta. I'm just going to do it as a little slivery thing there. 5.4 times 10 to the 5 meters. Oh, I should be using my rule thing here, shouldn't I? Like that. So what they are asking is that angle there. They are asking for you. So this is a real question. They're asking for theta, and you need to know what that angle is in radians, because it says radians there. And the way to work that out is, as I said before, The definition for a radian is S over R. So it is that divided by that, and you will get that nearly. Okay? So it's a very, very simple bit of mathsy, physicsy stuff, but wrapped in a sort of slightly difficult sort of way. Another word of warning here. I just thought of this. When it says about, can you see it's only one significant figure? Okay, so when they do that, what they actually want is for you to work it out to two significant figures to show that when that is rounded to one significant figure, in this case, it is 3. So if you do this and you say 5.4 times 10 to the minus 5, 10 to the 5 divided by 10 to the 11 equals 3 times 10 to the minus 6, you will almost certainly get it right. But you never know what the mark scheme might say. There was a question which was about this about word. And what the examiners wanted was you to do it more than the number of significant figures given in the answer, and then say to one significant, this significant figure, this is 3. Okay, I think for 2 marks, you would have got away with it. But sometimes, well, always it's worth doing that because that is the game that you've got to get used to. Okay, so that's an interesting one about the significant figures. Look at this. What are they playing at? What are you going to give your answer to? Molten lead, 3 significant figures. 2 significant figures, 2 significant figures, 3 significant figures, 2 significant figures, 3 and 2. Okay. You should give your answer to the fewest significant figures that you are given. So I would give the answer to this question to 2 significant figures because of that. That, possibly those 2 there, that is the limiting number. Okay, why they did that, I don't know. It should be 27 point something, 84 point, whatever. Anyway, so in your significant figures, if you give it to 4 significant figures, you might get it wrong. Probably won't. I don't know. We don't know what the examiner is actually saying, but make sure that you stick to, you always think, you look at your calculator display and it stretches off to infinity and you think, well, what am I going to write here? Don't write everything. That's pants. Write down your answer to within the same number of significant figures as the fewest significant figures of the quantity that you are given. I hope that makes sense. I hope that makes sense. So there's your significant figure stuff. Making estimates. Oh, I don't believe this. This was from EdXL. Are they having a laugh? Are they having a laugh? So this is what I said at the beginning. They are going to give you questions like, what is the volume of a house? And with practice, it can be fun to make up some questions of your own. Patronizing, only slightly. So let's have a look at this bog standard house. Sorry if it's your house. I'm sorry if I'm being rude. It is a typical house. It is a typical house. So let's have a quick think about this. I'm going to say that looks like 6 meters. 6 meters up to there. 6 meters. Oops. Okay. I mean, one floor to ceiling height is about 3 meters, 6 meters up to there. So I'm going to say that's about 8 meters, and it's probably, I don't know, 8 meters down there. Forget the roof. Then okay. Let me make that 7 meters because it's got a bit of roof in it. So 8 times 7 times 8 is roughly the volume of a house. Okay, and then you can make up your own. They say it's fun. I'm not particularly entertained by that, but that was an EdXL thing. So if you are doing EdXL, they might say, what is the volume of a typical house? Because they've said it. That was on their website somewhere. That was on their website. And later on, And another talk I do, I go through, when we do the practicals, I show you what you can get from your exam board's website. Have a look at your exam board's website. Have a good sniff around. Have a look at what the teachers access. There's stuff in there which helps teachers, which helps you if the teachers actually do it. But they're busy people. They can't do everything. So you are professionals. You have a good sniff around your websites as well. Okay, estimate the area under that graph. Oops. Estimate the area between line A and B. Okay, as I said before, you've got to sort of guess, make it into a nice shape or something for you to do that. But time is pressing on. I want to do this. This is an important one because in every maths bit of your specs, it says you must be able to use quadratic equations. You've done them at GCSE. They were great fun. You loved them. They were great. Okay, so we know that that is the standard form of a quadratic equation. Ax squared plus bx plus c equals 0. Okay, it's got an x squared term in it, it's got an x term in it, and it's got a constant term in it. So a, b, and c. X squared plus c. And this is given on your maths, on your formula sheet. It gives you the solution, the equation, so that you can calculate the roots, you can calculate, you can solve the quadratic equation. Okay. Now, sorry to remind you of your GCSE days, but they were good fun. Don't forget that a quadratic equation has got two solutions. So that is why it's got the plus or minus in it. It's got, so when you do b squared minus 4ac squared, that, then you add it to minus b, over 2a and get an answer. Then you take it away from minus b, divide by 2a and get another answer. You get two answers, two quadratic equations. And that is quite useful. I think it's an AQA, I don't know, but for some bizarre reason, it gives you the discriminated determinant. I've forgotten what it's called, beginning with D. Discriminant? Determinate? I've forgotten. Anyway, it does that. There is a question where this crops up, and it is in the SUVAT equations. Okay, there is one. You're probably thinking of it now, which is a quadratic equation, and you can solve it in some static equilibrium equations that you can derive. They are quadratic equations which you can solve. So we're going to have a go at solving a quadratic equation. Right, here it is. So we have a particle projected from ground level vertically upwards with a velocity of 20 meters per second. 20 meters per second, like that. How long does it take to first reach 10 meters? I shan't waste your time. S equals ut plus a half a t squared. That's a formula that we're going to use. Yes, it's a quadratic. It's a quadratic. Because what we have to do is to solve that for S equals 10. U is 20 meters per second. T is the time, how long does it take? T is what we're trying to find. We're trying to solve that equation for T. And A is the acceleration due to gravity. So if I rearrange that formula, we get a half a t squared plus ut minus s equals 0. So that plonks it into the form ax squared plus bx plus c equals 0. So we've done that. Then what we're going to do is to put our figures in. This is odd because by some remarkable coincidence, in the quadratic equation ax squared plus bx plus c, we've got a. Now, a is the number, I forgot what it's called, in front of the x squared bit. So there it is. So a, in this case, is our acceleration due to gravity. It's not a, as in ax squared plus 3x plus c. And then we've got our other terms as well. So I'll leave this with you for a minute because you've got to solve that. There is an additional problem, which is that we take upwards as positive. Upwards as positive. So u is going to be plus 20. A is minus 9.8. Okay, so I hope, I'm not going to do it for you. I hope you're getting the idea of what you can put into that formula to get your answers. And I say answers because the quadratic equation is going to give you 2, but it very interestingly says first reach 10 meters because it goes up past 10 meters and then it comes back down and goes past our 10 meters again. So there are 2 times where it will be 10 meters off the ground, and the solution of that quadratic equation will give you those 2 times. So they want the first one. So that was a multiple choice question. It's horrible. I'm not going to lie, it's horrible. There's a lot of maths in there. Okay, it looks simple, but believe you me, it is not. So if you like, have a go at doing that later on yourself. There's another question where this quadratic equation came up, and it's this. I'll just shut up for a minute while you read it. Okay, so if you don't mind, I'm not going to do this first question, but it is how long he's in the Air Force, like what we did before, but it's up and down like that. Nothing weird going on there. That is quite a straightforward, A is quite a straightforward thing. If you're not happy about it, you don't get 0.6, do it again until you get 0.6. There's no reason why you shouldn't get those questions right where it gives you the answer 0.6. Okay, so there he goes. Long jump, job done. 0.6 seconds. But he is traveling horizontally at 8 meters for 0.6 seconds. So how far does he go? 8 times 0.6, 4.8 meters. There it is. 2 marks easy. Okay, so that is quite a straightforward thing. Here's where it gets quadratic-y. O, R, R. So this is worth 4 marks. I'll just explain how you have to do it. What he does is he takes off from ground level, but when he lands, he is 50 centimeters lower. So what you have to do is use the equation there where S is minus 0.5 meters. He's 0.5 meters further down. Okay, that's what you have to do. So you put that into the quadratic equation where S is 0.5 meters. There is the answer. I'm sorry, that's the equation for finding out what that time is. So what you've calculated is an extra time. He's actually in the air for a little bit longer, and you can work out how far he travels. That's not enough. You've got to calculate the extra distance he travels. How much more than 4.8 meters is that? Okay, so you can do that yourself. It's fun. This is what the examiner said. Okay, so here we go. If you don't mind me saying so, I hate it when people talk when you're trying to read. Sorry. Okay, don't forget G is minus 9.8 meters per second squared. I didn't see that over there. Okay, don't forget that when you do your SUVAT equations, it is customary to think of going up as positive and the acceleration is downward. That's a common problem, apparently, but not with you. Okay, so here's part C. Part C was that quadratic-y thing. Okay, it was demanding. It was difficult. Hardly anybody got it right, but you will. So the best candidates, which is you, substituted the new vertical displacement minus 0.5 meters into there it is. There is our quadratic equation and solved the quadratic for the total time. Okay, so if you can spot it and you know your GCSE maths, then you should be fine. Look at this. There was a maximum of 9 for that question, and the average was 5.7. That's pants. Okay, so every little mark counts. When you eventually look at the grade boundaries for A-level physics, you will cry because they are so close together sometimes. So close together. So every mark counts. Every single little mark counts. And this is how you get those extra marks. Right. What's the time here? We got about 10 minutes. We got about 10 minutes. Let's have a look. Plotting two variables from experimental or other data. Why did I write that? Because when you plot your graphs, you must give your axes a title, and I'm just going to call it current. Let's say current in amps. Okay, that's GCSE stuff. You can do it like that if you like. The examiner will allow it, but you are professionals. You are better than that. What you should do is, that's the kids, what you should do is this: current divided by amps, because what you're actually doing is plotting a number. You're not plotting a quantity. You can't plot 5 amps on a scale. You can't. It's not possible. You can plot 5, but you can't plot 5 amps. So this is what you do. It's rather sneaky. You get your 5 amps, and to plot 5, not 5 amps, you divide by amps, and the amps cancels out, and you are left with the number 5, which you are entitled to plot. That's legal. You can't plot 5 amps. That is why you should give your axes titles like that, and then you put divided by amps. Okay, that is why you do that. Putting it in brackets is a bit sort of, that's what you should do. So I think it's worth knowing that, actually, because when you do your logs, it's super important to know that you've got to divide by your units. In the specifications, it says that zigzag line should not be drawn. It says that. And yet, I'll show you a question in a bit where they plot, they give you a zigzag line. Brings me out in a cold sweat. I do not like them at all. Right. A straightforward graph. Absolutely straightforward graph. Nothing interesting about that whatsoever. However, here's a more interesting graph. I put that there because when you do your Suvati stuff, have a go at using your spreadsheets. I just did that because I can use spreadsheets. Okay. When you plot your graphs, right, you never, ever get your 30 centimeter see-through ruler, plonk it on the first line, plonk it on the first point, plonk it on the last point, and join them up. That's awful. You must never do that. What you must do is plonk it on your graph paper, see-through, 30 centimeter ruler, jiggle it around a bit, move it up and down, slide it around, give it different angles, and so you set it so that it doesn't have to go through any point at all. What you are doing when you plot a line like that is you are doing some massive serious maths in your head. You are doing some linearly square fit programming in your head to try to get as many points on one side of the line as on the other side, And also the equal distance away, roughly the equal distance away. If you do statistics, you'll know about your linear least square fitting. And that is what you are doing in your head. You're actually computing those things as you do it. So when you've done that, then it says always, 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 it's going to say, determine the slope and intercept of a linear graph. I like linear graphs because you can find the gradients and you can find the intercepts of them. That's simple. But to find them, what you have to do is draw a big triangle. So I'm going to go from there. That looks nice. I'm going to go to that point because I like it. I'm going to go from that point up to that point there. Okay, my triangle occupies more than half of the page each side. Okay, that is a stipulation. That is what they look for. Your triangles have to be big, not piddly little. Oh God, I've seen these. Have you seen people do things like that? Okay, and that's a gradient. I'm going to do that there. No, 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 no. It's got to be the biggest triangle that you can to make the error in your measurement as small as possible. So there you go. You find your gradient. Now, I haven't put any units on here. Let me call that meters. Oops, let me call that distance in meters. And let me call that time in seconds because that's easy. The gradient has got units. The gradient is the units of that divided by the units of that. The units of that is the meter. The units of that is a second, but it's divided by meters per second. So the gradient of that represents velocity. What is the intercept? It's where it crosses the axis. There it is. No, it's not, because you noticed that I was messing about. It would be the intercept there if that was 0, but it's not. So how do you find the intercept when all you've got is a graph in outer space over there somewhere, a million miles from 0, 0? What you have to do is, and what they expect you to do, you can do some cleverer A-level mathsy stuff if you like, if you're comfortable with that. But what you do is, you know that that is the formula of the straight line. You know that that is the intercept. You have already calculated the gradient, so you know that number there. What they expect you to do, and every single question I've seen follows this process. You always find the gradient first, and then it says, what is the intercept? Well, the way you do it is you can take a point. I'm going to take that one. I have to look for a point. You can take any point that you like, but my eye has been drawn to that point there. Doesn't matter which one you use, and you put those numbers in. So you say 60 equals whatever gradient you've already calculated times 50 plus C. So you know what the gradient is. You simply put those numbers in and you then can find the intercept. That's how they expect you to do it. There's another way of doing it, which is a bit more A-level-y sort of thing, which you can use if you like. Right. Just realized I'm not quite going to get on to exponential functions. Doesn't really matter. If you can, spend a bit of time. If you're bored and you think, you know what, I'm going to do a bit of physics or maths, have a look at, on your calculators, there is a way of doing what's called linear regression, and it gives you the gradient and intercepts of graphs. There's a way of putting into linear regression mode, putting your what are they called, pairs, what are they called, coordinates, or the pairs, x, y, forgot what they're called, your results into a table, and then you press button and you get your gradient, you press another button and you get your intercept. It's worth spending 5 minutes and 2 minutes and 3 seconds doing that. So there's a YouTube video, 2 minutes and 3 seconds to use your calculator, your Casio, they're all the same, to be able to do that. It might save you a lot of time. trying to work out what the gradient is and what the intercept is. Okay, just use your calculators to do it for you. It's easy, easy, easy. Right. Oh, yes. Oh, yes. That. I'm going to do gradients and tangents and stuff. I've noted time. You're all there. Everything's great. Nothing in the chat. Okay. I'm just going to do this. So let's have a look. There is a nice graph. A-level question. That's an A-level question graph. And what I wanted to do was for you to find the gradient at 4 seconds. So I've done that. Have I done it well? I don't know. So the red line should touch the black line at 4 and should never cross it. Yeah, I'm happy with that. Okay, so at 4 seconds, the gradient is whatever it is. So you do your your stuff, you go from, I don't know, from there. Wasn't it working? Wasn't it working? From there down to there, and from there across to there. There we go. There's my triangle. And you work out the gradient, which is the rate of change of speed, which is the acceleration. Okay, that's pretty nice. The units of the gradient are the units of the upness, meters per second, divided by the units of the alongness, divided by seconds, divided by seconds. If I just do that, which is that, which is, oh, the acceleration. But hey, you knew that. So at 4 seconds, that is called the instantaneous rate of change of velocity, because that's what it was doing there. But the average rate of change is when it goes from up here. Oops, let me do this with a ruler. It goes from there down to there. Okay, and the gradients aren't quite the same. They wouldn't be really. But to find that average rate of change, it is 17.5 divided by 12, whatever that is. Okay. The instantaneous rate of change at the beginning is greater because the gradient is greater and it kind of levels off at 12 seconds. So the deceleration, because it's negative gradient, the deceleration at 0 is greater than it is at 12 because the gradient is a lot less. Right. I'm just going to have a little look at the next slide. It's 9:05. It's 9:05. We should start. Where's my mouse? There. Let me just get rid of all of that and look at the next one. Same sort of thing. Okay. I shall stop there. Hope I've enjoyed that. I hope you've enjoyed it too. Okay, maybe in the catch up on Monday, tell you what I'm going to do. In the catch up on Monday, come along again. I'll carry on from here because I really want to do the exponential functions so that you get an idea of what they are before you are actually hit over the head with them later on in the year. Right. If you've got any questions, of course I will stay. I always stay after. If anyone wants to unmute and ask a question or put something in the chat, then I'll be happy to answer it. I'll wait till everybody's gone before I turn off. Have a lovely weekend. Hope it's not too cold where you are. We might get some snow down here in Bristol. Hope you're nice and warm, and I'll see you on Monday. And I'm thinking school starts pretty soon, unless it snowed off. Well, hey, good luck. Have a nice weekend. See you Monday. Ta-ra. See you. Cheers. Cheers.